Welcome to the webinar, Choosing the Right Antenna for Today's Testing Requirements. My name is Belinda and I'm editor of Interference Technology, the creator of EMC Live. EMC Live is an online 3-day event hosted by Interference Technology. This event will include roundtables, webinars, and videos on everything EMC related, and there's no cost to attend. Join us for our other webinars this week. This webinar is presented by Tom Molyneux. As an author and an RF engineer, Tom has been in the EMC industry for 20 years, both as a supplier to the industry and a hands-on program manager, achieving EMC compliance for new products. This webinar is sponsored by AH Systems, Inc. AH Systems was established in 1974 and manufactures a complete line of affordable, reliable EMI test equipment. Their individually calibrated EMI test antennas, preamplifiers, current probes, and low-loss cables satisfy many test standards, including CISPR, MIL standard, FCC, EN, VDE, IEC, and SAE. With over 95% of their items in stock and next day on-time delivery, AH Systems is the company to contact for your antenna requirements. This webinar is one of many this week. To check out our others, visit emclive2015.com. Recording of this webinar will be available on our website. This webinar will be interactive. You'll be able to ask questions, and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the box on the right-hand corner of your screen. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or report an issue, click the hand icon. We will discuss the topic for 30 minutes, followed by a 10-minute question and answer session. Now Tom will begin the presentation.
Thank you, Linda. May I just confirm, do we still have 30 minutes, or we got to get the whole thing done in 20 minutes?
You can go as long as you need.
Okay, thank you. Thank you, audience. Please bear with me. Sorry about that technical hitch. And so today's talk clearly is on choosing the right antenna for today's testing requirements. And today's testing requirements usually mean high frequency tests. And there's a couple of things that come into play with high frequency tests, and that's particularly the beam width of the antenna. That is, if you're illuminating a calibration plane, then you get bending within that plane, and the external calibration points will see less of the field than the very center of the calibration plane. Now, what I'm going to push on you here is visualization, because if, like me, you like to see what's happening in terms that as you design a system and you want to look for any problem areas, then visualization is the way to go. And I'm going to use that same visualization on showing the beam width effect and how you can transpose the calibration plane onto the polar plot provided by the antenna manufacturer. And then I'd like to do something that I think is quite novel, and that is incorporate that beam width effect actually into the system-wide equation. So you see an overall final system gain that you can then use to calculate the power required for this gain. So basically there we are. It's going to be in the main higher frequency field generation. So you won't see any bicons or anything like that. It's all going to be horns or log periodics. And then we're going to spend some time on the impact of the antenna gain and beam width as they come into play with high frequency testing. A good place to start is at the beginning. So here we have the standard field strength calculation. And there it is in the right-hand corner. E, in the field strength in volts meter, is equal to the root of 30 times V times G all upon the distance D. It's worth spending a few seconds just looking at this picture. There's D, the distance between the antenna aperture there and the position of the field probe. That thing on the right is supposed to represent a field probe. And that is pretty much set as by the standard that you're working to, either 1 meter or 3 meters. And then you have the antenna itself, which has an attribute called gain. And you have the power going into the antenna, which is power, the RF power in watts. Now, it looks a bit grim, that, especially to new people, they're thinking, what the heck, that's a fairly heavy equation. But if we do a little bit of work on it, we can actually simplify it some and find out what's happening here. And so the root 30 PG all upon D can be separated into two constants. The constant D, which is determined by the standard you're working to, the number 30 root of, which by definition is a constant. And if we call those constants, group those together and call them K, now this is refusing to go down one, and I don't know why. Seems to be a day of hitches. I apologize, everyone. It appears that now the PowerPoint is refusing to move on. And I'm not sure why. The computer itself hasn't crashed because the mouse is moving around freely, but for some reason they're refusing to progress along the screens.
Hi, Tom. We have a suggestion.
Are you there, Belinda?
Yes, we have a suggestion. If you just exit slideshow mode and then go back in, that might do it.
If I, okay, what do I do? What do I exit? Because when I press escape key, it won't
hit
let
escape.
me. I'm hitting escape and nothing's happening. Oh, very odd. It's saying, do you want to leave the webinar? Did I say yes to that?
No. Nope. You want to stay right here. No.
Sign in again.
No. It doesn't have anything to go with.
Okay.
We see your screen. Oh.
Aha.
Okay.
Something happened.
I believe it's your computer. It might be running slow. It's not a GoToWebinar issue.
Okay, so yes, so let's go back to that screen that you're looking at now. So the field strength is equal to root 30 PG all upon D, and that can be separated out to constants to root 30, and the D is set by the standard. Let's press progress. Yes, it went. Okay, and that goes to a constant times the root PG. Now we can look at this a little deeper, and given that the standard sets the volts per meter at 3 meters, we can set that as a fixed voltage, for instance, volts per meter, for instance, 18 volts per meter. There we go. And so there we have it. K, we now have a constant with a suffix E, which is a constant field, is equal to a constant, which we separated out, times the root of P and G. And now that allows us to look at a lot clearer at what this equation is actually doing. If the left-hand side is a constant, that means the right-hand side is a constant. By definition, it has to be. And so that means that the root PG, and indeed PG itself, is indeed a constant. Let me give you an example. If P was 10, and G was 10, and in the bracket there, that came to 100. However G changed, P would have to mimic it and change in opposite sense. So, for instance, if G moved from 10 to 5, P would have to move from 10 to 20, given a product of 100. I think you see where I'm going here. So however the gain changes, the power will change to maintain within the brackets there the same number. So that makes the whole thing a lot clearer. One thing I should point out, though, you see the field probe there, and that's at the bore side. The bore side is the dead center of the main lobe of that horn there. If you were to drill a hole in the back of that back plate there and pierce through the antenna, you would see the field probe, and that would be along the board side, the point of maximum power in that direction. And so now we've tamed that equation a little bit. Let me see what's actually happening, particularly when you put in the standard distance and the standard volts per meter. Let's have a look what we mean by P. P itself is the power, the RF power actually going into that connector there. It has to be going into that connector for this equation to work. Now, that's simple enough. What about gain? Gain's a little more complex. The gain is an attribute of an antenna. And it's the number of times, it's how many times better it is than an isotropic antenna. Well, what's an isotropic antenna? If you imagine a point source of certain RF power, and it's emanating power in all directions, and as an expanding sphere. And if you see that red line there, that red line represents a wavefront as the waves go out, and that's one particular wavefront. And as the wavefront travels forward and forward, and this is in 2D, in actual fact, try and imagine it in your mind as 3D, it's expanding as a sphere, not as a circle. And up it goes and gets further and further away. And here we have tried to represent it in 3D for you there. And so what you have there is the power density at that distance. And I've got the S stands for power density, suffix ISO stands for an isotropic radiator. It's equal to power, the P power you started with right at that small dot there, divided by the area of that sphere as it gets bigger and bigger and bigger. And as we know, the area of a sphere is 4 pi r squared. And that's measured in watts per meter squared. And that's what an antenna references to in terms of its gain. So if we look at a non-isotropic radiator, and here we have our own antenna again. And I've put in there, because just for the sake of it, a gain of 10. And you can see that you kind of squish down your sphere. You squish down your sphere, and you push more power in one particular direction. And that direction is the bullseye direction. And at the end of that arrow there is where you put your field probe and measure the power density at that point. Again, it's in watts per meter squared. And if you look at the small equation at the top there, the power density of the antenna is equal to 10 times the power density of an isotropic, if the isotropic was fed with the same power. That's a way of describing an attribute of an antenna. Now, if we're looking at this in 2D, here's a picture of it, a more realistic one of it in the 3D. This is courtesy of CST, who allow me to use their software. They've got a very powerful software package. And what I have here is I drew these squares, the 4 brown lines on the front, so you could get a better feel for what you're looking at here. But what it is a section of waveguide, and I flared out every wall of that waveguide into a square, as you can see there. And when you put RF into that waveguide, feed the waveguide, then you'll have RF power emanating out of the front aperture there. But I think you can see that most of the power is along that bullseye I described earlier. And if you look on the right-hand side there, where it tells you how strong things are, red is the strongest there is, blue is the weakest there is, and I think you can see that most of the RF power is heading along the bullseye direction. Now you notice that the units are dBs, actually dBis, and RF engineers use dBs all the time. Now you may hate them to begin with, but if you use them often enough, you'll find there's a certain beauty to them, and you'll see some of that beauty during this talk. So how do we convert the regular linear gain that we described a few seconds ago into dBi? Well, it's simple enough. It's calculated as the gain in dBi is equal to 10 times the log of that ratio of the power density of the antenna over the power density of an isotropic radiator if it was fed with the same power. And again, if you were to look at a manufacturer's data sheet, it would be listed in dBis. And when they provide plots, lo and behold, the information is in dBis again. Now, if we look at this particular plot here, there are two groups of curves. The one we're interested in is the bottom group, that cluster of lines there. And just so we know, if we look at the key there, we can see that the gain at 3 meters. And that, by the way, is what we're going to concentrate on today. 3 meter testing, 80 volts per meter, nominally at the calibration plane. The regular 61,000-4-3, that regular standard there, which is 18 volts per meter. If we home in a little bit on that plot of gain, and I'm arbitrarily going to choose designing a system going to 10 gigahertz, because probably in a few years' time, that's where we'll be going, to above 10 gigahertz or above in today's testing. That's the trend is upwards. And what I've done there is I've put some lines in to make it easy to see what the gain is at the testing frequency we're going to be looking at today. Well, we're going to be designing today, which is between 1 gigahertz and 10 gigahertz. Let me read those yellow lines for you. The first vertical yellow line you see reading left to right is marking 1 gigahertz. And that coincides with let's count it for you, 5, 6, 7, 8 dBi. 8 dBi. The antenna gives 8 dBi at 1 gigahertz. Then if we go to the right and look at the right vertical line that coincides with 10 gigahertz, then go left at the intersect and we read 10, 11, 12, 13 dB. 13 dB again. And so I think we've pretty much described gain there. Let's rearrange this equation because we're designing a system and we need to know how much power to put into this antenna to achieve our 18 volts per meter at the bore side at least. So by simple rearrangement of the equation to make P the subject, we end up with the power required at the antenna connector is equal to the distance squared times the volts per meter squared, all upon 30 times the gain, and that's the linear gain of the antenna. And if we put those numbers in, we end up with 3 squared times 18 squared over 30 times 6.3. The 6.3, and the more you do this, the better you get at it, is what is the linear gain for 8 dB. So we're looking here at the 1 gigahertz data provided by the antenna manufacturer, and so that has a linear gain of 6.3. Do the calculation. And for us to achieve at 1 gigahertz at 3 meters, 18 volts per meter, we need 15.4 watts. Now that, of course, is the power at the connector. Rather poorly drawn there is supposed to be a cable, and it's a fairly long cable, and the power you put in at the end of the cable, this end of the cable, will not be the power that comes out of the connector because the cable will have loss associated with it. And so the power going into the cable will be greater than the power reaching the antenna, so we have to take that into account in our system. And this more schematic-y sort of drawn picture shows you'll need the block on the left-hand side is supposed to represent an amplifier. On the right, there's the antenna we've been using all the time. The antenna's inside the chamber, as shown by the pyramidal absorbers there. And the cable goes via a bulkhead and in the chamber. And I think reasonable numbers would be 3 meters from the amplifier to the bulkhead, and another 5 meters from the bulkhead to the antenna, which will be on the tripod. Those are reasonable numbers. So I alerted you earlier that, particularly for me, and I recommend for you, is to make things visual so you can see what is happening with the system overall, all the way from 1 to 10 gigahertz. And this is particularly important because you want to be looking for any suckouts whereby misfortune, a dipping gain in the antenna happens to coincide with a high loss, high frequency cable loss, and by visualizing it, you can see immediately if you're going to hit a problem early on. And so the I took that from the plot you saw earlier, where I put the yellow lines, intersecting lines to identify, and then I put all the crosses for similar intersections, and I joined them together, and there is your antenna gain, all the way from 1 to 10 gigahertz, the system we're designing. And there is your cable loss. Now, I have loss in brackets on the left-hand side there because technically, minus 1 dB of gain is, of course, 1 dB of loss. But it's the cable, this data I got from the AH website. They've got this clever little thing where you put in the length of your cable, the type of your cable, and then it will tell you what loss you will get for 1 gigahertz, 2 gigahertz, 3 gigahertz. I went to the trouble of doing that and got that data plot there. And this is what I mean by visualization. Here's the system-wide performance, the net gain of the system you're designing so far, using this antenna and using that particular cable. Now, we're talking about 10 gigahertz, so there's going to be some loss at the connectors, particularly that bulkhead connector, well, that all connectors actually. So I put in a little bit. I couldn't do less than 1 dB because it would be too tight, but I put in a little bit of loss for that net gain, for the connector loss. And so the dotted line there, the dashed line there, represents the antenna gain minus the loss introduced by the cable and minus the loss introduced by the connector. And I call that the worst case gain, system gain, because we're talking system at the moment so far. We've got some to go. Now we come to the main theme of this talk, and that's where at high frequencies you have to take into account you're likely to have higher gain, and high gain invariably means narrow beam width, and that causes an impact. So let's look again at the rather rudimentary horn antenna made from flared waveguides. And there we have it. And I'll read it for you because I can probably see it better than you. I'm looking at the information on the bottom left there, and it says a frequency of 1 gigahertz. And try and remember this. It has a gain at 1 gigahertz, this very rudimentary horn, of 12.74 dB. And we know now that's actually dBi. How does this rudimentary antenna, flared waveguide antenna, work at 10 gigahertz? And try and remember this first picture. There's 10 gigahertz. And when I read the gain in the very bottom line there on the left, I read 24.89. That's a phenomenal increase in gain. Something you don't really want, but it's very rudimentary antenna. And there's a price to pay. Now, this is a webinar, so I'm not sure how soon your screens refresh. But I'm going to go up back to the original 1 gigahertz data, count to 4 seconds, and come down again, and hopefully it won't look too messy on your end. So going back to the first one, and look how big the lobe is. There it goes. Mine went, I'll give it 1, 2, 3, 4. Hopefully yours is there. I'm now going back. 1, 2, 3, 4. Hopefully you saw the trade-off there with this very poor antenna, where basically you've got a tremendous gain improvement, however, at the cost of beam width. So if beam width is so important, then antenna suppliers must give you data on beam width. So because as a designer, you need to work out whether this beam width is going to do what you want it to do. This antenna is going to do what you want it to do. Lo and behold, this is a screenshot of the AH Systems website. And it shows a polar plot, and it describes 3 different radiation patterns for 3 different frequencies. And the frequencies are, and try to remember this, the red one is 1 gigahertz. The blue one is 9 gigahertz. And the green one is 18 gigahertz outside our remit, but it's still of value to us in terms of learning what's happening here. So let's close in on this polar plot. And ignore, if you can, just for the moment, the red, the blue, and the green trace. let's look what we've got here. It's a full circle, only a segment of it here. It's a full circle, and the 0 degrees is marked off in degrees. And the 0 points to the bore site we've been talking about, where the maximum field strength will occur, where the maximum power density will occur, is along that 0 degree point there. And then as you move, then it's marked off in 5 degree segments. So I'm counting, you count with me, 0, 5, this is going clockwise, 0, 5, 10, 15, 20, 25, 30, etc. And then anti-clockwise, 355, 350, but it's 5, 10, 15, 20, so forth in the anti-clockwise direction. And equally important is if you look to the left of the 0 bore sight line, I'll read this for you because it's a little bit fuzzy. You have 0, the outer circle. Then you have -3, that's -3 dB, -6, -6 dB, -9, and so forth, all the way down to minus goodness knows what lost in the noise floor. So basically, you can plot on here the power relative to the bore site. Relative to the bore site, if I was to move 5, 10 degrees and look at the green line, it's dropped about 1, maybe 1.5 dB, that green line, at the 10 degree marker. So there's actually quite a lot of information here if you know how to use it. And so I took to the trouble to mark off where the 3 dB points are, because they define, it's a figure of merit for an antenna. The 3 dB beam width is where the beam power is dropped to half power at its limit. And I've drawn those in yellow. And so 18 gigahertz, we now have the beam width. And this will be backed up on the manufacturer's tabular data on the spec sheet. But this has, let's count it, it's where it intersects. So we've got 0, 5, 10, I'm going clockwise here, 15 degrees, and 15 degrees other side. This antenna at 18 gigahertz has a beam width of 30 degrees. And we can do likewise with the one at 9 gigahertz. Let's count those off, going clockwise again, 5, 10, 15, 20, what is it, 23, 24, let's call it 24. And it's the same on the other side. So at 9 gigahertz, this has a beam width, half power point beam width of 48 degrees or thereabouts. And then the final one. This is for 1 gigahertz. And it has a very nice beam width of 10, 20, 30, 40, 80 degrees. Why am I saying it's a nice beam width? Well, this system has a job to do. The antenna has to illuminate this calibration plane. Now, familiar to most, it's a 16-point equidistant measurement points where you put your probe in these 16 different places. And the intention is to have them all at the same field strength. But the standard realizes, of course, that would be pretty hard to get it at the field exactly within the 18 volts per meter. So what it does allow is, it says any point here can be 18 volts per meter minus 0.0 dB. That means it cannot be less than 18 volts per meter. And plus 6 dB. That means it can be twice as much. Now, I need to point out here that while designing this system, we're not going to take into effect room effects, etc. We're going to assume we've got an ideal chamber with no room effects, and therefore we won't have to discount 4 of the measurement points. We want all 16 of those measurement points to be between 18 volts per meter and 6 volts per meter, and that's what we're designing this system to do. And so there we are. Probably 8 dBs at the moment because it's easier to read, but we'll make it between 18 volts per meter and 36 volts per meter. But again, you'll see the beauty of dBs a little bit later. So let's see what we're asking our antenna to do. We're asking it to illuminate this zone of interest. This zone of interest, if you look at this picture, we're now looking at the calibration from the plane from the side, and we can see those 4 points from the side, and we can see the antenna. And our area of interest is the area that illuminates the top point and illuminates the bottom. Anything outside of that, I mean above or below the uppermost and the lowermost point, we don't really care about. All that's going to do is be absorbed by the chamber walls or bounce a few times and then eventually absorbed. What we're interested in is that zone of interest, the calibration plane. But it's a bit of a trick. You have to be wary. Antennas don't give off square radiation patterns, square section radiator patterns. They're going to be round or elliptical, somewhat elliptical. And so you can easy to be fooled to think just take between the two extremes, the vertical extremes of the measurement points there. In actual fact, you have a circle, as you can see. More likely an ellipse, but for our purposes, let's go with a circle. I think you can see that, in fact, the diameter of that circle is greater than top-to-bottom distance or side-to-side distance of our calibration plane. In fact, according to simple geography, the a squared plus b squared equals c squared, it's going to be √2 times the vertical, or either the A or the B. And I should point out I have supporting notes, so I don't have to dwell too long on this, and thank goodness given the technical hitches we have. Where there's a little bit of background mathematics, I've produced some supporting notes, and they're on the AH Systems website. And if you go onto their homepage and then click on technical notes, the very first item on there is the supporting notes that give you things like the a squared plus b squared and what they turn out to be, etc. And so now if we look again from the side of our calibration plane, and please note at the very top of the circle and the very bottom of the circle, I put 2 X's. And so now if we look from the side, we can see where those 2 X's are. So in fact, it's a trick to think it's the top and bottom calibration points is the zone of interest. Our zone of interest is as shown there. There's our 3-meter distance as required by the standard. There's our calibration plane as described by the standard, but our zone of interest is there. And the math's done again in the supported notes, but that, of course, theta there is the angle whose tangent is equal to opposite over adjacent, which is 1.06 meters over 3 meters. And that comes out to 2 theta, that's double it, to give us our beamwidth, of course, is 39 degrees. I won't call it a beamwidth, it's more of an angle of zone of interest. So let's look again at the data supplied by the manufacturer and the 3 frequencies and the 3 beam formations of the radiation patterns. And the brown lines there represent our zone of interest. It's supposed to be 39 degrees. On paper it looks 40 degrees, but I think you can see what's described there. And to the right of the rightmost line, we don't care. That's going to hit the absorber wall. To the left of the leftmost one, we don't care either. Now, wouldn't it be nice if it was possible to move those points of interest at the calibration transpose them onto that polar chart? So, for instance, the top cross and the bottom cross, which are the circular illumination of the zone of interest. And let's not forget they actually pass through calibration points and they're not just out there in the air, they're required. And what about those other 4 points, those calibration points? Wouldn't that be nice for them to be transposed onto the polar chart so we can get better visualization of what's actually happening? Well, lo and behold, we can. If we identify in terms of angles, because of course it's a polar chart, in terms of angles where each one of those important points are, and we determine θ1, θ2, and θ3 as shown there, then we can in fact transpose that onto our polar plot. And there it is. The brown lines will of course intersect with our 2 red crosses. And there are the angles described. And again, the calculations are in the supporting notes, are the calibration points of interest. Now this actually holds quite a lot of information. If you look at it, you've got your greatest power density, your greatest volts per meter at the bore sign. And then with distance to right or left, you can see, let's use the blue line. you can see that the illuminating power is dropping off as you go rightwards towards the rightmost red cross. So for instance, let's say at the extreme where the brown line crosses the blue line, we have, what would you say that's 2 dB? We have 2 dB of loss. So although our bore site might be at the intended volts per meter, in fact, at the right cross, and don't forget these crosses actually represent a circle that pass through calibration points, will be 2 dB down. Now, there's a small intermission here where I just want to give you the basic idea of the effect of beamwidth. Let's suppose we have an antenna that just so happens has a beamwidth that fits our zone of interest completely, absolutely. And let's not forget what we mean by beamwidth. It's the half power point. Now, in terms of half power, that is, the half power will be the volts per meter divided by √2 because it's power and so forth. And so what we're looking at there is E, the bore site field strength, and then E upon √2 represented by that red circle where the field strength has dropped because it's now at the 3 dB limit, the half power limit of our antenna, which just so happens to have a beamwidth that fits exactly around our zone of interest. So if we put numbers in there, we get 18 volts per meter. We can't be less than that if you remember. We have to be minus 0 dB plus and a maximum of +6. There's a certain window that these points must fall in. So we've got 18 volts per meter there. The center has to be between, the center point has to be between 18 volts per meter, cannot be less, and 36 volts per meter, cannot be more. But if we do the math, and again it's in the supporting note, we end up with 25 volts per meter. Now what does that mean in terms of our system design? Because we're going to have to select an amplifier to power this. What it means, sorry, I was out of step there with the talking and the thing. So there's your 25.5 volts per meter. Your amplifier is going to have to provide the antenna with the power to produce that 25.5 volts per meter. We originally had 18 volts per meter in there. So now the calculation changes from not 3 squared times 18 squared over, but 3 squared times 25.5 squared over. And that comes out to 31 watts, which you'll have forgotten the previous one, which was 15.4 watts, is exactly double the power we originally thought we would require to obtain 18 volts per meter. So that break off there was basically to describe what the impact of beamwidth. Now that we're into high frequency testing. Now that we have narrower beamwidths and higher gain, we need to take the beamwidth into account. So if we look again at our requirement, and bearing in mind we have the situation where we've defined our zone of interest and discount anything either side of it, it would be nice to also define our degree of freedom in terms of the allowed parameters, that is, we cannot exceed +6 dB. So we look here again at our polar plot, and if you remember at 0 degrees where it hits the calibration plane, that is our maximum power density, that is our maximum volts per meter. And if we bear in mind that it cannot exceed 6 dB higher than that, then I marked the 6 dB there, if you look carefully, with a yellow arrow. The first circle is 0, then the next one down is -3, and then I mark with the yellow -6 dB. And if we draw that line in, pretty much we've got our limit. What we're looking at there is, you see the red radiation pattern and its beamwidth, its slope shape. and then you see the blue, and then you see the green. You see they get narrower and narrower and narrower. What that yellow line means, it's a keep out area. Below that yellow line and within the segment marked by the two brown lines is a keep out area. You're not allowed to be, your beam width is not allowed to be, your beam is not allowed to fall within that area. Because by definition, if it's 0, you're at your minimum, you're at 18 volts a meter. You must have exceeded 36 volts a meter for the beam, which is going to end up on where those red crosses are. It cannot be more than 6 dB away, because it would then be in excess of 36 volts. So I've artificially drawn in a beam. It's not very good, but it's not too bad. And that is pretty much the narrowest beam you'd be allowed to have. Not a brilliant shape, but it's not too bad from when you look at how the shape of the other ones are. It's probably not far wrong to consider when you consider it again. And if we now draw in the lines where it crosses the 3 dB marks, we have, for our system, we've defined the minimum beam width we're allowed to have, which comes out at 28 degrees. So now, we've actually gained quite a lot of information here. We've got a large don't care area. If it falls outside this slice of cake defined by the two brown lines, we really don't care. And we've defined a keep out area, whereas no matter how hard we try, if there's more than 6 dB difference between what's at the ball side there and what would turn up at those two red crosses, we've lost already. There's no way we can fall within the limits defined by the standard. And this is quite useful information when you're designing, because people are quick to blame things on room effects and so forth, and you are in fact allowed to drop 4 of those calibration points, allowed by the standard to do that. But where I'm going here is, if basically, in basic theory, it cannot be achieved, when you put it in that chamber, it can only be worse. It cannot get better. You're on a hiding to nothing. You can't win. So there's a visualization of the calibration plane and how it's been illuminated and the particular limits and don't cares, etc. I think we've got a better, also the absolute minimum beam width we want to see on there. If this antenna has a beam width of less than 28 degrees, then you're getting very, very tight, and it's going to be unachievable. Your goal is unachievable. You're pretty much wasting your time. Now, we've got this nice visualization in front of us, which tells us a lot about what's happening in this system. Now, wouldn't that be nice? Remember when we first put together visualization over 1 to 10 gigahertz of the overall system gain? Wouldn't it be nice if we could further transpose that information onto the beam width? And I'm going to call this, I don't know if other people have done this, it's something I thought of a few years ago. And just as you have cable loss, where you have to increase the amplified power to compensate for that cable loss. Well, when you think about it, you've got that bore site strength, but you have to increase the power, because of the two red crosses, you need more power in order to bring them up to 18 volts per meter. And that to me is a system loss. So I'm going to call that a beam width loss. Let's see if we can't factor it in. So I've shown you that when I was reminding you that if the power, if we have to increase the power, these lobes going towards the red crosses, then we have to introduce more power from the amplifier. So I'm calling that a loss. So let's get back to where we were with looking at our overall system loss. Originally, we put together because we were looking out for dangerous suck-out points where, again, we would not be able to achieve our goal. And it was looking pretty good. And we got the worst-case system gain there of, I'm going to say, 6 dBi. And we've got, and there's the original net gain loss, which is composed of the amplified gain, the cable and connector loss there. So we start with that. And now we introduce our beamwidth loss. That'll involve me going back to this. If we look, there's only actually two traces of interest to us here. The red one, which is at 1 gigahertz, and the blue one, which is at 9 gigahertz. It would be nice if it was 10 for our purpose, but we can probably extrapolate. In fact, that's what we'll do. So if we follow from our 0 point on the red curve, and let's go clockwise, 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 until we hit our red cross, and with the definition of our zone of interest, we can see that the power density has dropped. What would you say that was? Each one of those boxes represents 3 dB. I'm going to say that it's dropped 1 dB. So we need to compensate for that. So we'll call that a loss. Then if we look at the blue one, and do the same thing, go right, go right, go right. Wait until it intersects with our brown line there, limit of the zone of interest. I'm going to say that's 2 dB, given that's 3 dB box. So we now have, at 1 gigahertz, we've got a beamwidth loss of 1 dB. And at 9 gigahertz, we've got one of maybe a little under 2, but I'm going to call it 2 because we're actually going to test. Our system requires 10 gigahertz. So here we are, we're starting with where we were, with a visualization of our overall system performance. And now if we add our beamwidth loss, as just mentioned, at 1 gigahertz, there's your 1 dB of loss. And at 10 gigahertz, there's your 2 dB of loss. So is that 2 or 3? It looks like I've got 2 or 3. Anyway, this isn't being exact, this is more visual. You can see that if you drew in your beamwidth loss there, and then if you calculated your system gain again, that is the net gain originally, taken into cable and connector losses, and then introduce your losses due to beamwidth, where you have to increase the amplified power in order to compensate for that. You'll end up with the series of red crosses there and the brown line. And you'll see the worst case system gain is actually dropped now to about, I would say, 2.5 dB if you follow that blue dashed line back. So you're taking quite a hit in terms of system loss. So now, if we were to introduce into the same equation for how much power you need to get a certain volts per meter strength at a certain distance, the rearranged one for power there, which is d squared e squared over 30, but instead of g, which is the gain of the antenna, I've actually substituted g, the gain of the system. And if we put those numbers in, and I can leave it at 18 squared if you think about it. You can call it 18, but because I've compensated for the higher power that's required at the bore site to allow 18 volts a meter at the peripheral measurement point. I've actually already factored that in. And so that comes out as 54 watts. So I think, assuming I haven't made any deep fundamental errors, and I don't believe I have, I think you can see that's a way of visualizing, not only in terms of when you're designing a setup for this, if you're designing for high frequency to 61000-4-3, but also even if you're using and troubleshooting a system, with that visualization, you've got a far better understanding than basically flying blind, as many of us do at this time. Now, there's one more thing we need to look at in terms of beam width and narrow lobes, etc. In days of old, before 1 gigahertz testing, you would have things like a biconical, which is a derivative of the dipole, and it would give off a radiation pattern that's shown there. And the power coming from the amplifier and then through the antenna would be radiated pretty much in all those directions, illuminating the 4 walls. So the wall behind, the 2 walls, one of the walls with the door and the other wall, opposite wall, also the wall that has the calibration plane, or that's shown here, the unit under test. And even if the unit under test fully reflected back at the antenna all of the impinging waves, because that area is only a tiny part of the overall area being illuminated, very little of power will be seen back at the amplifier. However, nowadays, with much more directed antennas, I think you can see here, and again, this is that rudimentary horn antenna, that I haven't angled this very well. If that hits at 90 degrees, if that impinges at normal, much of that power will be reflected straight back at that antenna, will be captured by the antenna aperture there, and end up in the amplifier will see a lot of the power it puts forward. And so something that has to be borne in mind now with these very directive amplifiers, because we're up in gigahertz way above, is that what wasn't a problem becomes a problem. Now that's Mother Nature for you. What she gives you in one hand, she takes away in the other. But I mean is what she gives you in one hand. When you had lower frequency testing, you had a lot of reflective power that the amplifier had to bear. But that wasn't because I just described, because the reflection from the EUT, that was because the antenna was such a bad match. The RF power would travel from the amplifier along the cable, see the bad match at the antenna, and come thundering back towards the antenna. And that's those days, thankfully, have gone, because above 1 gigahertz, with these antennas, you get far, far better matches, far better. And so Mother Nature has taken that away from us. However, now she gives us that in one hand, now she takes it from the other hand. The reflective power has now become a bit of a problem, because, as you can see there, there's a good chance that if it's a large EUT with a beautifully screened front panel, as we would design into it, because we don't want impinging RF to get into our system, a lot of it could well be bound straight back into the aperture, and the amplifier will see it. Thank you, Mother Nature. So what do we have? We have a situation where by starting with your antenna gain across the band of interest that we're designing, and factoring in one by one the different losses, in particular, as I've introduced now. I don't think I've seen other people do that regarding Beamwidth as a loss. Putting that in as a loss too, you can get an overall gain. Well, there we go. We get an overall gain, and we can get that system-wide gain, plug that into the power required equation, and come up with the actual power that we need. Also introduced here is the idea of taking what is actually quite a lot of information in these polar plots that's supplied by the antenna manufacturer, and then sectoring it off into the zone of interest. So the brown lines there are don't care lines outside that area, because the RF isn't hitting the calibration plane, so why should we care? And the yellow line is a defining factor beyond which, if your beam is so narrow that it crosses that yellow line, then you're on a high need to nothing, no matter how you try and fix this in a real-life chamber with all the room effects that they have there. You will never be able to fix it, because you've already, under ideal, perfect conditions, overrun the limits given by the standard. There, ladies and gentlemen, thank you for listening in, and I really do apologize for the issues getting started here and run a little late. I run it a little bit faster than I wanted to, because I realize some of you have broken off and probably have to leave. So, but hopefully we'll have some time for questions.
Hi, Tom. Thanks so much.
Hi.
We have run out of time, unfortunately, so we got to wrap this up. But if anybody does want to send in any questions, we have gotten a few. Any of the ones we've gotten in, we will send along to Tom. And if anybody wants to send us more, you can email us at info@interferencetechnology.com. Tom, thank you again for your time and expertise.
Thank you, Belinda, and thank you, audience.
Please join us next year for EMC Live 2016, which takes place next April. A recording of this webinar will be available on our website, emclive2015.com. We will also send a link to all participants shortly. Thank you for attending.